So I'm Dr. Hines. I'm the nuclear engineering department head here at the University of Tennessee, and welcome to our graduate colloquium series. This is a little bit of an abnormal day. We had a presenter who was going to present today that had a conflict and had to cancel kind of at the last moment. So I sent out an email yesterday asking if any if any faculty had graduate students that they wanted to jump in and give a presentation, and no one. There were some conflicts there. There were some conferences going on, a lot of other things happening, so no one stepped up. So I guess I'm the last man on the bench. So I'm going to give you a presentation today about our fast neutron source and some things that are going to be happening in our new building. I thought this may be of interest. Let me go ahead and share my screen. Get up to the top here. So this, I just made the title Department of Nuclear Engineering Fast Neutron Source. And most of you, a lot of you have probably seen this slide before. This is a slide of our new engineering complex. Pasqua Nuclear Engineering Building was built in 1925. It got demolished, I don't know, almost 2 years ago now. And Estabrook got demolished at the same time period. Berry Hall got demolished. They cleared out this whole area next to the stadium there, and we're building a $129 million new engineering complex. It's going to house, I'll jump to the next slide. It's going to house engineering fundamentals. Engineering fundamentals is really on this left-hand side. It's kind of, the building is kind of built in 4 sections or 4 quadrants. You have this one up front to the left, and was just going to be engineering fundamentals, but now the dean's suite is going in there too. So communications, the dean, the associate dean, all of those functionalities will be on the 4th floor on this left side. The back main part of the building is mainly laboratories. This front right section that's sticking out, this is the nuclear engineering department. So nuclear engineering department really has all their administrative functions and students and faculty in this right-hand side sticking out. Back behind it are the nuclear engineering laboratories, and it's scheduled for completion this coming summer. It's been a long road to get there. What I'm going to talk about today is what's happening in some shielded facilities. So you can all see this truck that's kind of up next to this big opening. Our high bay is going to be over there. We have a really nice large high bay, and next to the high bay is our shop. And then behind the high bay and the shop are these shielded facilities. So we have 23 new nuclear engineering laboratories going in the new building. And I'm going to talk about this, mainly about this research laboratory 14, this fast neutron source. The other thing is, anybody that wants to interrupt as I'm talking, this will be fairly casual, so feel free to stop me and have questions. So fast neutron source, what does that mean? Well, we're going to have a core, and the core is going to be reconfigurable, and it's going to have the ability to give the same flux spectrum as a fast reactor. And why would we want to do that? Well, there's a problem with uncertainties of certain interactions, so certain cross sections up in the fast neutron space. So if you look at this top right plot here, this green or the red and the blue line, that's the spectrum you get from a thermal reactor. Neutrons are born fast, they thermalize, and then we have this thermal spectrum down here where most of the power comes from. These two kind of humps on the right, these are the spectrums for a sodium fast reactor. So this is energy. You see they're fairly high energies. And this is basically your intensity. Below it here is a cross section with respect to energy, and the energy matches up with the graph above it. And we see that we have a thermal section, an epithermal section, a fast spectrum. The blue line is the actual cross section. The red line here is the uncertainty. So down in the thermal space, you see that there's a very small uncertainty. The uncertainty is, under 5%. If you get up to the fast space, you see uncertainties that go anywhere from 15%, all the way up to 60 or even 70%. So if we don't have good data of understanding, a really good understanding of how the neutrons interact with materials, then we can't do a very good job of simulating it. And just like the aerospace industry, they don't go out and build a new airplane. They first, simulate it and use modern engineering tools to do the design. So we have several reactor concepts, these advanced reactors that are operating in the fast space, and we need to use nuclear cross sections that go into the modeling and simulation codes that then allow us to design these next generation reactors. And if we have a lot of uncertainty in our cross sections, then we have a lot of uncertainty in our mod and sim, and there's going to be uncertainty in the design. And this higher uncertainty in design makes the designers have to put in more conservatism. And that conservatism makes the plants more expensive and less economically competitive. So the goal here is to try to assist these advanced reactor designers so that they can make more competitive and less expensive designs. You might say, what are these fast reactors? Well, here are 7 of them that I just found on the internet. TerraPower has a molten chloride salt fast reactor along with the sodium reactor. Elysium has a chloride salt reactor. We'll see here in a couple of slides that the chloride salts have some real challenges when it comes to cross sections. So we have, we have lead fast reactors, sodium fast reactors, molten salt reactors, some gas cooled fast reactors. We're really focusing on the lead, the sodium, and the molten salt. So this is just kind of a case study that comes out of a published article from some researchers at TerraPower. And this is their traveling wave reactor, their sodium cooled reactor. And they state that the uncertainties of many parameters are higher than is desired, motivating additional efforts in cross-section measurements. So they're basically, and when I've been up at DOE and I've talked to some of the people up there, they're kind of responsible for the cross-section areas. And they say that, they commonly, or at least this one executive up there, commonly got called by TerraPower saying, when are we going to get better cross sections? Because that'll really help out their design. These uncertainties in the cross sections are causing uncertainties of void worth plus or minus 147%, temperature feedback coefficients plus or minus 138%. So it's a real challenge when they're trying to design reactors when they don't have really good data. This is another example of the molten chloride fast reactors. In 2011, the red line here was our knowledge of the cross sections. The blue line is now our present knowledge of the cross sections. You can see that they've changed a lot. You have all these resonances that were poorly understood. And some of these resonances, they actually calculate through theory. And then they go in and they try to use a facility like Lance out at Los Alamos and try to actually measure these different cross sections. But the Lance facility has lots of cross sections to measure, so they can't get to all of these that are going to be useful or they're really needed for our advanced reactors that are operating in the fast spectrum. There's also needs for better cross sections and for NNSA and detection, forensics, transport. So in nuclear safeguards, and just lots of the areas. There's actually a report that came out of Berkeley that was nuclear data needs and capabilities for applications. And most of these focused on NNSA needs. So NNSA has a huge stake in this too, and they could do a better job with some of their missions if they had better cross sections. And I'm not going to go into any detail in that. But so what are we doing to try to meet this need? Well, when we started planning for this new building, we thought we probably have the opportunity. I mean, how often does anybody get to build a new nuclear engineering building? And then we had the opportunity to have some new research facilities incorporated into the design. And we talked to NASA, we talked to lots of different entities and tried to figure out where is there a national need? You know, how can we affect that national need? And what could we maybe build in here? So if we look in the lower left, these are the heavily shielded facilities. So the heavy shielded facilities, there's a linear accelerator room where there's a 9 MeV LINAC. Dr. Hayward is working on that lab. We have the fast neutron source room, where the fast neutron source will be down here on the left. And it's a long skinny room because there may be some opportunities to do some differential cross sections, to put a beam line. This room I think is about 70 feet long, 16 feet wide, 20 feet tall. It's got a big crane, a 5-ton crane that can move big shielding pieces and move other things back and forth. There is actually a roll-up door where we can get from the high bay through a hallway right in here, and we can take a forklift and move any large pieces of equipment into either of these laboratories, whether it's the accelerator lab or the fast neutron source lab. You enter this through a doorway from the hall, going into kind of this radiation laboratory access room. So if you ever had possible contamination, that's where you'd swipe in, swipe out. That's where you'd have your security, you'd sign in, those types of things. If you turn left there, you go to the control room. So this control room will basically control the LINAC. It'll also control the fast neutron source. If we continue through another small concrete wall, we get to where our senior, well, I guess junior and senior laboratories will have some experiments. We're going to bring the graphite pile back from across the river. The approach to critical facility will be here. And if you go on through that, you get into where we store our sources and our natural uranium and other things that might be radioactive. Some of these walls are 5 feet thick. In fact, they poured this whole section in one big pour. So this was, about 28 or 30 feet wide. You take the 70 here and you add on another 50, so this is a huge pour. And this shows them getting ready with the rebar. I think there's 5 different layers of rebar that goes into that cap. That cap, when they poured it, they actually cooled the aggregate. They cooled the gravel with liquid nitrogen, because when you pour concrete, it's an exothermic reaction when it sets up, and you can't have the temperature change from the middle of the concrete to the edge of the concrete above a certain amount, or you can get cracking. And these are shields. You don't need cracking where you can have radiation or gamma streaming coming from your radiation facilities. So it was really interesting how they had to do that pour, and then all the instrumentation that they had throughout that concrete to make sure that the concrete was meeting the specifications. So the fast neutron source core, I'll talk a little bit about that here. It's a core. We don't call it a reactor. And when we first started talking to NRC about licensing this core, we really didn't want to go through the more stringent licensing for a reactor, which is in the 10 CFR 50 series. We wanted to be limited to the 10 CFR 70, which is to have and maintain and use special nuclear materials. So basically enriched uranium in our case. So as long as this core doesn't go critical, and as long as it doesn't produce enough heat that you need any type of heat removal system, we can just license this as special nuclear material and not as a reactor. So that's how we're moving forward. It'll be a neutron-driven subcritical system. So we'll have a DD neutron generator, which will be the source, and then we'll have material in the core, which will amplify the flux and change the flux or shape the flux so that we get the flux that's desired, the flux of a fast reactor, whether it's a sodium or a lead or a molten salt. There's an oscillator, and that's how you do the differential cross sections. You actually move the material into and out of the core. So the oscillator will be on this. If north is at the top, will be on the east side. That's where the oscillator and the experimental volume is. On the west side is where the neutron generator sticks into the core. We have a pneumatic transfer system where we can put materials into the core. We can pop them out of the core, shoot them up through this 5.5 foot thick concrete cap and into a counting room that's located right above, almost right above the core. We have a beam line that we want to be able to put in place and design and put in place in the future. For both, the beam line will be used for differential cross sections, and the oscillator is going to be used for integral cross sections. And the transfer system will really be used for activation analysis. You know, the goal is to make this highly flexible and reconfigurable. So to make it so that if we want to use it today for and simulate a molten salt reactor, and in 2 days we want to switch it over and simulate a sodium fast reactor, and a couple days after that we want to reconfigure it and simulate something else that might be important in the NNSA space, then we want to be able to do that. So several of us went to France in Cadarache, and they have a facility called Mazurka. And I went there with some researchers from Oak Ridge and from Idaho National Laboratory. And we looked and got a nice tour of the Mazurka facility. And this Mazurka facility is an air-cooled facility. This is kind of their core, and it hangs up in the air, but they can lower each one of these tubes, and they're called wrapper tubes. They're 4 inches by 4 inches by a meter long. And they fill that with different rodlets of different material, some square platelets of different materials, so they can load each one of these tubes, each portions of this core with a different type of material. Then they had an accelerator, and the accelerator produces the neutron source. And they were doing really some accelerator-driven system research. It's called MUSE, when they were looking at using accelerator-driven reactors to burn spent nuclear fuel and for some other things. So we looked at that and I said, okay, you know, it'd be great to be able to integrate this flexibility into our design. And this was our first design concept. We had I think it was in 2017, we had a senior design group and we said, okay, I want you to design a fast neutron source. They actually designed it a little bit different than this, but it ended up being a source where we have kind of a 5 by 5 array. The core is in 3 sections. Each section has this 5 by 5 array. Each one of these boxes in the array, we call a cassette. You can think of it as a shoebox. We can fill that shoebox with materials, just like they did at Mazurka with the wrapper tubes, and we can change the materials and we can build this core. We built it in 3 places or in 3 sections so that we could have shutdown plates that slide in between these sections. So if you were, you know, our original design was going to use, you know, just under 20% enriched uranium-235 rods. So we had basically, in this case, we had 1-inch diameter rods put into a matrix with lead. So we were looking at a lead fast reactor. And to make this thing go to 0.95 K effective, it was taking about 4,500 or 5,000 pounds of 20% enriched uranium in a rod format. The neutron generator sticks in on one side. Here's where the neutron generator sticks in. The oscillator and the experimental volume is over on the other side in the middle. So it was just these stacked cassettes. Now, when I went to NRC and we talked to them about this, well, actually, we went there and we talked to them about this design, and I learned more about the different categories of facilities. A Cat 1 facility is really a facility that has highly enriched uranium that may be weapons grade. You have a Cat 2 facility, and this is general. There's some how much of the material do you have, but generally, if you have quite a bit of material, if you're above 20%, or if you're below 20% enriched, then you go to a Cat 2 facility. So I guess we were looking at being a Cat 2 facility, and you look at the security requirements, and basically it takes barbed wire, layered defenses, and a 24-hour guard. You know, a 24-hour guard is going to cost you, at least $300,000 a year to have a person stand there 24 hours a day. That's not a cost that we really wanted to have. So we had to look at how can we reduce our uranium from 20% to 10%. So if we went from 20% to 10%, we might have 10,000 pounds of uranium, and that's a lot of uranium, and that's going to be really expensive. So we looked at, if you don't want to use as much uranium, maybe you need to go to a thermal spectrum. A thermal spectrum, the cross-section for fission is about 500 times the cross-section for fission of a fast neutron for uranium. So 235. So I was part of a team that was looking at the versatile test reactor. And one of the proposals for the versatile test reactor, which is going to be a fast reactor with a really high flux for materials irradiation, we won't have that high of a flux. We can't really do any type of materials degradation and materials irradiation for degradation analysis in our facility. But if you looked at VTR, they were looking at one of the designs looked at a fast thermal coupled facility. And they referenced this facility that was back in the Netherlands. And there's been a couple of these. This isn't the only one, but this was called STEC. And STEC operated between 69 and 73. It had both a fast section and a thermal section. And it was developed and designed. It was the coupled design was to reduce the amount of uranium they needed. And that was kind of what we needed, is to reduce the amount of uranium. But they were using it to find cross sections for fission products, really for the development of the European breeder reactor. And they had an oscillator, and they used the inverse kinetics method, which is exactly what we're looking at doing. So, a lot of times we kind of wrap ourselves back and do something that was done before. But right now, there is no place in the United States where you have a fast flux that's similar to one of the advanced reactor designs, at least. So we took this concept, we took the Mazurka concept for the flexibility and the STEC concept to try to reduce the amount of uranium needed. And we ended up with thinking that, okay, if we put a thermal zone over here on the right-hand side and put uranium plus a moderator to thermalize the neutrons so that so it'd be much more reactive, and then maybe have a fission plate here in between, so these neutrons would hit that fission plate, cause fission, and basically just be a big thermal booster for the fast side. That's what we were looking at. For the thermal side, we didn't need as thick of uranium rods because the thermal neutrons aren't going to penetrate or be able to diffuse as far. So here we had about 1/2-inch diameter uranium rods that we thought would be about right. We used the 1-inch diameter uranium rods in the fast side, and we moved it down to a 0.975% enriched uranium. And by doing that, we were able to reduce the amount of uranium by quite a bit, at least a factor of 2. If you look at the K effective of the thermal side by itself is 0.88. The fast side is 0.60. The coupled experiment, when you couple those together, we have a K effective of 0.95, which is what our goal was. And this is the MCMP flux profile. We see that the thermal flux is very high over in the thermal side. Each one of these color changes is a factor of 2. So we have over in the experimental volume, the thermal flux is much lower. Here's the fast flux. It's very high right there at the neutron generator. And then you had a factor of, 2, 4, 8. So a factor of 8 lower over in the experimental volume. But we had at this point, we were kind of trying to optimize the fast to thermal flux ratio. We wanted a high fast flux and a low thermal flux. we weren't looking more specifically and looking at the resolution of the spectrum. But then we said, is this really the best design? And we talked to the people at BWXT and Y12, and they don't do a lot of work with making uranium rods. They make uranium plates, right? And I thought, well, these rods don't have to be, don't have to have the ability to heat up and cool down like the real fancy plates that you make. They don't have to be able to take, hot sodium onto it. We don't have the corrosion problems. We don't have the heat transfer problems. All that we need are some really cheap rods made. And they said, it's kind of like if you go to a Porsche plant and you say, I don't really need a Porsche, but just make me a Volkswagen. Cost a lot of money for a Porsche plant to make a Volkswagen. It's a lot easier for a Porsche plant to make a Porsche. So they explained to me that they'd be better off just making plates. And we thought, well, what if we took each of these cassettes, each of these shoeboxes, and we loaded plates into it? So we had 1/2-inch plates. We have a 10-inch long cassette. We put 20 plates into this. And you do the same with all the other cassettes, And then we thought, well, what if we had let the computer, artificial intelligence through genetic algorithms, what if we let it decide where to put all the plates? And when we did that, it actually reduced the mass by a factor of 3 and improved our fast to thermal flux ratio by a factor of 3. So I'm not going to get into how the genetic algorithms work in much detail, but basically you have a generation, like there's a generation of people here on Earth, and they mate and reproduce, and they have some mutations, and then they create a new generation. And that new generation, if you look at the survival of the fittest, the newer generation will be made by the people who survived the saber-toothed tigers and those types of things. And your next generation should be, bigger, faster, stronger, smarter than the generation before. In this case, we might have 100 designs in a generation. We analyze those designs. We take the top 10 designs and we let those 10 designs reproduce, mutate, and grow into another generation of 100 designs. And we take the top 10 and we use those. So the good parts about the design get carried forward.
Professor Hines?
Yes.
I was just curious about the mutation process. How is it enabled?
Yeah, it's just a random process. So maybe you have maybe 1% of the plates, you actually switch from material A to material B or material B to material C. So it's just a random mutation that goes into your core. So if there's a more optimal design that you haven't looked at and that's not in any of your parents that get moving on from one generation to the other, this allows new things to come into your design that you didn't originally have. So that's how the mutation works. But here in this case, we went from our old gray-haired man design to this other design with using the genetic algorithms. And one thing that we see is the poly, the red, actually moves into that middle section. At first we thought, no, we can't have any of those thermal neutrons get in there. We could go supercritical and we could have this problem and that problem. But you run it in MCMP, it's like, no, this is the most optimal way to do it. And this, we had a 92% higher fast to non-fast flux ratio, 120% higher fast flux per source neutron. So by allowing the computer to move the plates, it did a much better job than we were able to do ourselves. And the people, I need to give credit to the other people that work on this. Vlad Sobes, when we started this, he was still at Oak Ridge. And then he came over to become one of our faculty. But this is some of the types of work that Vlad does. Vlad came from the nuclear data group at Oak Ridge, so he understands the need for nuclear data. And of course, he understands reactor physics very well. And then the graduate student that's done most of this work is John Peavy. And he has just dug into this and just, he must love it because he gets so much work done every week and just really making huge inroads and providing big, really great contributions to the field. So then we said, well, we really want to not only just have this high fast thermal flux, but we want to have a good we want to get the spectrum so it looks like the spectrum of interest. And if you have a spectrum, if you have two spectrums, there's something called representativity. Here's the word here, spectrum representativity. And that tells you how close or how similar two spectrums are. So we wanted, in this experimental volume, we wanted to move these materials around, and then now we want to match the actual spectrum. So this red spectrum is the sodium fast reactor spectrum. But we have two different objective functions. We want to maximize the representativity, and we also want to optimize the amount of flux. So the higher the flux, the better the numerical, the numerics of the system are. You don't have to run an experiment as long. So if you have 10 times the flux, your experiment only has to run 1/10 as long. So we want a high flux level, and we want a very good representativity. You can think of the representativity as a correlation function. It's how, so it ranges from 0 to 1, with the 1 being perfectly representative. So in this type of a genetic algorithm, these blue dots are different parents that went from one generation to another generation. And we're looking at the parents, the ones that are out on this front are the ones that we're interested in. So if this is representativity, these all have about the same representativity. And in this case, about 0.95. And then this is flux. So you can get a higher flux, but you give up representativity. Or you can get something very representative, but you don't have as much flux. So they're competing objectives. And we look at this front, we call this the Pareto front, and we always choose the parents that are basically along this Pareto front, and we try to push that Pareto front out further and further. And maybe the best core here would be this one right here, where we have a great representativity, we have a high flux, because the representativity of that one is about as good as the one below it. But these are the different fluxes that we got from these different parents. And the representativity here is anywhere from, if you had a high flux, but you have a low representativity, that would be this one on this end. We have one on this end, then we have the one in the middle. Those are these three that are being shown. But high representativity and still a pretty good flux. So let's talk just quickly about licensing. What would you have to do to license this? Well, you have all this low enriched special nuclear material, so you have to go in and get this 10 CFR 70 license. The main parts of that license is your organization, which also includes your training, criticality safety. You have to make sure that you're not going to go critical under any condition that could be hypothesized and has at least it has a limited probability of actually occurring. You don't have to think of things that would never occur. Fire protection. And let's think about fire protection. So this whole building, this whole new building, the state fire marshal, requires us to have it sprinkled, have a sprinkler system throughout the whole building. Do we want a sprinkler system in this room that has our fast neutron source? If we put water into this core, it's going to thermalize those neutrons. Your K effective is going to jump up. You could have a criticality accident. So I remember early on telling the people, if you put a sprinkler system in there, I'm putting an umbrella underneath it because it's not going to get on my core. And they said, well, we'll just put a sprinkler under your umbrella. So it kind of went that way. But after a while, we explained it to them. We said, this has to be a moderator-free zone. We can't have any moderators in that room that could cause a criticality accident. And we talked to other people who've had similar types of vaults where they can't have a moderator. And what they do is they say, okay, if you have a fire in there, you have these 3 or 4 foot concrete walls, you shut the big shielded door and you let the fire burn itself out. And we had a fire engineer do the calculation, and it burns itself out very quickly and doesn't cause any type of a problem. So it'll be a moderator-free room. It'll also be a room where we have to administratively control any type of flammables. We're not going to store paint in there. We're not going to store wood. and filing cabinets and those types of things. We want to make sure if there's ever a fire in there, it has minimum amount of fuel. So we didn't have to sprinkle it, and that's how we've taken care of the fire protection. Environmental protection, that's really radiation protection. You have to prove that you have the proper shielding, that no one from the public can get any type of a dose really above background. So that's again, MCMP modeling, building the right shielding. You have the concrete walls, but we actually have designed in some close-in shielding, and I'll talk about that a little bit more. Security, security. You have to have rapid response. If we have this uranium in there, you have to have intrusion detection systems. Anybody that goes in there has to have an escort, or there have to be two people together. We have, I'm not going to go into detail on our security system, but that's a main part of the licensing tasks. Material control and accountability. You have to be able to determine if someone has taken some of your special nuclear material. You can't go in there and inventory it once a year and say, sometime in the last year, we've lost 10 kilograms of 9% enriched uranium. You have to have methods where you can fairly rapidly determine if anybody has improperly moved your special nuclear materials. And then I guess there's environmental protection. That's where you're looking at, are you right next to the river where you could flood? And we have to think about that because we are kind of near a river. But then the radiation protection shielding, we have to think about that. So how do you shield a fast neutron source? First thing you do is we put a reflector around the core so that we can increase the flux. And that reflector should be something that doesn't have usually it's a heavy, high atomic number material. It doesn't have a cross section. We don't want something that's going to become activated. We don't want to have to run this thing and then wait 3 months before we can go in and change the experiment. So, stainless steel has a lot of materials, zinc and other materials that get activated very easily. We don't want to use stainless steel. So, we're going to use carbon steel, which is a little bit better for that. So you put a reflector, in this case, there's a 10-inch reflector. And then, anything that gets out of that reflector, you want to kill. You want to get rid of those neutrons. So, how do you get rid of neutrons? Steel isn't a very good shield for neutrons. Let me see if I have chat, if anybody's answering it. Paraffin, yeah. So when you have neutrons, first thing you have to do is you have to slow them down, and then you have to capture them. So borated poly. So we slow it down with the poly, which is kind of what Greg says there. You slow it down, and then your boron has a huge capture cross section. But when it captures it, and it turns into, lithium and an alpha, it gives off gammas. So now you got rid of a lot of these neutrons, but you made a whole bunch of gammas. So then you need another shielding on the outside of that to get rid of the gammas. So we end up with a core sits in here. We have 10 inches of steel, 4 inches of borated poly, and then another 6 inches of steel to shield the capture gammas. So when you're trying to shield neutrons, usually you have to use some type of a layered method. You need to get rid of the neutrons, and almost anything you use to get rid of the neutrons is going to create some gammas. Then you have to get rid of the gammas. So that's our basic shielding idea. We've had lots of senior design projects that have helped us move into the right direction of developing all the systems related to this. At first in 2017, we had our fast neutron source initial design. We also had that group design our approach to critical facilities. Some of you may have seen it. It's down in the basement of the nuclear engineering building. It'll move over into the laboratory, the student laboratory spaces in that shielded design that I showed earlier. And we made that approach to critical facilities so that we could put a neutron generator in it. And we could basically use it as a thermal neutron source, right? And we can use it to get some operational experience. We can use it to understand how we do K-effective monitoring, how we can do, develop an oscillator system. We've used it for this automated flux mapping system, pneumatic transfer and counting system. We could use it to throw materials into it, pull them back out and count it. So we've had lots of senior design projects over the last 5 years. And this last year we had Dr. Peavy led a group doing criticality safety analysis, gave us a lot of good information there. We worked with Y12 on doing the safeguards design. How do you make sure that you secure and safeguards the materials? Dr. Woods worked at least once, maybe 2 different times on a shutdown system. Dr. Miller has been working on the fast neutron flux mapping system. I've been working with a couple different years on the pneumatic transfer system. So lots of really good designs have come out of this. And I think the students have really enjoyed it because they felt like they actually designed something that someone is going to use in the future and it's going to be useful. So we've written quite a few proposals, and some of the reviews, like last year we wrote an NEP IRP, a $5 million proposal to get funding to finish this up. And we get reviewer comments such as, you don't even have the enriched uranium yet. Where are you going to get that enriched uranium? We've talked to NNSA, we've talked to Y12 and BWXT. We think we can get the uranium. It's going to cost probably $3 million. But it's a long timeline. It would take, you actually have to probably spend a year to do your license application. NRC is going to take 1.5 years to look at your license. And then maybe at that point, when they give you a license, maybe at that point you can actually start getting the fuel made, which will probably take another 1 or 2 years. And a lot of these proposals only last 3 years, so it's really hard to actually get the funding and then have a facility operational within 3 years. So there's this long timeline. So we've come up very recently with looking at revising our development strategy and starting it off with natural uranium. And we have a senior design team this year to say, okay, if we didn't want to use the enriched uranium, could we use natural uranium? Could we still match the flux profile, match the spectrum as well? And what would what's the negative of that? Well, the negative of that is we have a flux level reduction of about a factor of 10. So 10 times longer experiments, but we can still match that spectrum as well as we could with the regular license or the enriched uranium. But what's it do for us? Well, we don't have to get a Part 70 license. We don't have to have safeguards and material accountability requirements that we would with special nuclear material. We don't have to have these engineered safety and shutdown systems. We don't have to have a criticality safety plan. There's no way we're going to go critical with natural uranium. We don't have the special nuclear material security requirements. There's just all of these things that that you're required for your license. Most of those things we don't have anymore. We still have to make sure that no one gets a dose above background, but we're at an order of magnitude lower flux, so that's really easy for us to do. So we've already ordered our DD neutron generator. We've written a proposal through the NEUP infrastructure grant, so hopefully they will fund us. If not, we're going to keep doing it, anyway. We can't stop, and we can only control what we can control, and we have to be responsible for ourselves. We can't expect someone else to fund us. We can't put all of our eggs in that basket. But when we went to natural uranium, here's one of our recent runs that John Peavy did. We can still get a 0.99% representativity. See, way out here, almost a perfect one. This is the sodium fast reactor. The one in the blue is the natural uranium, and the one in the gray is if we had the enriched uranium. So the natural uranium is going to have some higher thermal fluxes. But what's interesting is the representativity is still almost perfect. And in this fast area is where we're most concerned, and we can match the flux almost perfectly. So the good news is that we can go to natural uranium. We could get this thing probably built in a year. We could get it operational in a year. We don't have to get the Part 70 license from the NRC, and we don't have to do all of those things. And then we can build our expertise. We can learn how to do the experiments. We can learn how to do the foil counting. We can build the oscillator. We can do all those things. And then it'll be much easier to move from that spot to the spot where you want to change out the natural uranium with enriched uranium. So that's what we've decided to do here over the last few months. And I think the stepwise design makes a lot of sense. I'm kind of running out of time. So this is an experiment that shows if you have, I think there's 20 or 30 half-inch slabs. So this is a 1D optimization experiment. We have void, poly, fuel, and sodium. And these are the parents of the last generation. These have the highest representativity. These have the highest flux. The source is put here. So think of each one of these rows as a design. And you can see that you can move to a very high flux. Here's flux. If you have a high flux, you have a low representativity. If you have a high representativity, you have a lower flux. So there's that trade-off. And we're actually saying this is our experimental volume. This is where the tally is being kept. So if we put this neutron source here, if anything goes the wrong direction, it gets thermalized by the poly and then hopefully creates more fissions from the fuel, or at the least, it gets reflected back in towards this volume. If you look between this area, between the source and the tally, if you don't care about representativity, there's a lot of void in between there. If you care about representativity, it takes a lot of sodium because it's a sodium cooled reactor, and it's the cross sections and the interaction cross sections of the sodium that makes the flux have a certain spectral shape. And then if it gets past the tally, it wants to reflect back. So this fuel and this poly would reflect it back. So that's just kind of an interesting run that we've done over the last month or so. So in summary, we've designed this fast neutron source. It's going to be in our new $129 million engineering complex. The goals are that we have, neutron fast cross-section uncertainty minimization to promote better modern SIM for next generation reactors, fast reactors. In the future, when we move up to enriched uranium, we also have a goal of doing nuclear criticality safety training in there. Now, if you want to do crit safety training, you have to go out to Sandia. I went to the course there, I don't know, maybe a year ago. It's a great course. But the people at Y12, the people at Oak Ridge would like to have something local that they don't have to send people way out to New Mexico. It's under construction. It's going to open in 2021. And we've developed these new AI-based methods to optimize the design. So you could optimize the design, load it, run the core. You could say, okay, give me an optimal design if I want this other spectrum. It'll say, okay, here's how you have to load it. We could reload it in a day or two and have it completely reconfigured to give us a different design. Thank you for your attention. I'm happy to answer any questions.
I have a question.
Okay, Robbie.
How did you, I guess, what kind of constraints did you impose on the geometries during the AI-informed design? I guess how manufacturable are some of these optimum designs?
Yeah, so that's what, so we may not, we did constrain the design quite a bit. When we tell the computer to optimize it, we basically say, here's your 3-section 5x5, matrix of boxes that hold, 20 1/2 inch, 6 inch by 6 inch, 1/2 inch thick plates. So, and we're getting, it's kind of cool. We're getting all the sodium from the Zipper facility out at Idaho. So we're going to have this stainless steel clad sodium. Then we can get, lead plates. That's about $10,000 for the lead plates that we want. We get steel plates. Now we have the natural uranium rods. It's not the perfect, rather than, we probably would have been better off with 1/2-inch thick plates, but we'll have to start off with these 4-inch by 1-inch cylindrical rods that we can still load into our cassettes. But we were constrained in that we said we're not going to change the structure. We have the same core structure, and the core structure is an aluminum structure, but we allow the AI to determine which plate goes in every holder. You know, if you have 75 cassettes and 20 plates in each cassette, that's 1,500 different core material positions. And if you have 4 different materials, your combinations and permutations is just unbelievable. But the genetic algorithm can kind of get you around that curse of dimensionality and allow you to get, you know, the genetic algorithm is an optimization routine. It's not a routine that guarantees you to get the optimal core, but it moves you towards, you know, an optimal core. But so everything is manufacturable. You know, we're going to manufacture things that are 6 inches by 6 inches by 1/2 inch. So that's really easy for us. Did I answer your question?
So you basically told it that the geometry couldn't change much, and so it was constrained to optimize based on, you know, this cassette geometry, and there was very little variation on that.
Yes. And
Okay.
geometry is actually big enough that, you know, this outer ring of cassettes, you know, it may just be that's a reflector too, to do what we're trying to do. So we could have, and we have actually, and Dr. Sobes is looking at, you know, or he has these AI methods, and we're doing it for the transformational challenge reactor, where it actually changes the shapes. And he gave a presentation, I don't know if it was earlier this semester or last semester. You can go back on the archives and look at it, but it actually changes the shapes of the materials and the shapes of coolant channels so that it reduces any temperature variations across the coolant channel, reduces thermal stresses of the core. So in some cases, you can allow it to change the geometry. In our case, we fixed the geometry. Now, is this the perfect geometry? Probably not, but is the Mazurka geometry pretty similar to this? Yeah. You know, if you made it more cylindrical, it would probably have less leakage and would be a little bit more optimal. But how do you manufacture and put all these plates into a cylindrical geometry? It'd be much more difficult. So you kind of have these criteria that the manufacturers want to give us plates. And so you look at how do you use plates to build an optimal design.
Cool. Thank you.
Okay. I think John Peavy's here in the audience. John, did you have anything to add?
No, I think that covered it pretty well.
I have a question.
Yes.
Yeah, so I understand how with the fresh fuel with natural uranium, how you could avoid 10 CFR part 70 with the special nuclear material, but I'm just wondering how you're dealing with and what the requirements would be once you have your plutonium in the irradiated core.
Yeah, so this is natural uranium. At the flux levels, we're really not gonna breed any measurable amount of plutonium.
Okay.
I mean, we're looking at flux levels that are maybe 10 to the 7th. If you look at a research reactor, you know, like at NC State or someplace, it might be at 10 to the 11th. You know, there's 1,000 times different. So maybe, you know, we'd have to run our thing for 1,000 years to breed as much plutonium as they would in 1 year. And then I think that you know, we only have what, 0.7% uranium in it, and they have, you know, they might have 19%, you know, enriched uranium in what they're doing. So when we move into the 9.75 enriched uranium, we'll have to worry about the uranium, but I don't think we're going to have to worry about the plutonium. We just won't have high enough flux levels to really ever be breeding any. We never have to worry about replacing the fuel it'll never burn out at these flux levels.
Got it. That answers my question. Thank you. And then one more quick question. When you talk about like either lead, sodium, or salt coolant, can you explain that a little bit more? Like, is that one of those will be determined and decided, or is it a plan to somehow interchange?
It is. So, yeah. So if you want to do sodium, you go and you get the spectrum of a sodium reactor. And that's what we've done here. So we have a spectrum of a sodium reactor. And then we tell the genetic algorithm, hey, move the materials around so that I match that spectrum. So I maximize that representativity. If I want to load it for a lead fast reactor, I'll get the spectrum of a lead reactor. And I'll say, okay, now optimize it for this. And it's not going to be at temperature. But one thing that Dr. Sobes thought of early on when he was at Oak Ridge is you have this oscillator over here in this experimental volume. Your cross sections change with respect to temperature. So what if this oscillator actually had this heater in it? So the material that you're putting in and out, you get it heated up to where it's at the same temperature as a sodium fast reactor. Then you don't have to worry about the reactivity changes or the cross-section changes as a function of temperature. So not only are we looking at an oscillator to calculate cross-sections at normal room temperature, but we're also looking at having a heater there so it can calculate the cross-sections at a temperature of interest.
Yeah, that totally makes sense. Thanks.
Yep, thanks, Karen. Anyone else? Well, I hope this was instructive. I know it's always exciting to hear about what's going to go into your new building and what you might have access to in the future. And that was kind of my goal here. And my goal was also to help you think about some things. How do you shield neutrons? Just some of these basic things that, you get into your specific research so deep. It's nice to kind of step back and say, and look at some more broad concepts. So hopefully I was able to do a little bit of that and bring you back to some of your undergraduate nuclear engineering education and reinforce some of those things at the same time. I appreciate everybody's time. I'm sorry we didn't have the speaker who we had signed up for. I hope I did an okay job, and you guys have a great week. Take care.